recording it now. Better late than never. Yes, this B is in the 144's place, and the 1's in the 12's place, and the A is in the 1's place. But B stands for 11, so it's 11 times 144 plus 1 in the 12's place, and the A stands for 10. So that's base. Base is bigger than 10. And a very famous base is base 16, otherwise known as hexadecimal. It goes 9 A, B, C, D, E, F before for 10 through 15, and then 16 looks like the number 10. Computers use base 16 also, and that's mainly because you might have seen, like in the old days, like a website, they would like change like the background color would be like AF13B or something like that. That was a base 16 number. It's very easy to convert base 16 to base 2. And that's why they also use base 8 in computers sometimes. Otherwise, it's called octal. Okay, so skill number 1 for today, well, skill 1 is just the existence of different base systems. Number 2 is how to convert from one base into base 10. But the next skill is a little trickier, which is converting in the other direction, starting with base 10. So 101, this is like a binary number, but it's actually a base 10 number, into base 6. Now, there are 2 ways to do this. There could be more than 2 ways, but the way I like to do it is I first figure out how many digits my answer is going to have. And I do that by writing out the place values for base 6. Now, as soon as my next place value, which is 216, is bigger, it's bigger than 101 already. So this number is only going to have 3 places. And here's sort of the sneakiest way to do this. We ask ourselves, we work from left to right, how many 36s are there? Well, we could do that just through subtraction. So I can take off 136, and I could take off another 36. So I could take off a total of 2 36s, and I put the 2 there. But I still have this 29 left over, so now I start subtracting 6s from that. And I count how many, 1, 2, 3, 4 of them. And then finally, this number that's left over is the number of 1s. That's that's the way that uses the most fundamental math. It just uses subtraction. Now, if it's a really large number, that subtraction method might take a long time. So how could you save a little bit of time on the subtraction method? You could type it into the chat. How can you like save a little time? And that's right, through division. If you have a calculator handy and you do 101 divided by 36, you get 2 point something, and that 2 would be the answer. But you wouldn't have the remainder, sorry, 101, you wouldn't have the remainder, you'd have a decimal remainder. So you'd have to like do 101 minus 2 times 36 to get this 29 here, because some calculators have remainder function. So it still be kind of annoying. And this is a very good way. I like this way. There is another way that I'll point out, but let's have you do one now. So this 358, this is actually 358. Can you convert it into base 7? And I'm going to let you guys chat about it. I'll mute myself. Okay, and I do see a couple of 1021s in there. It is 1021, and I'm going to show you, though I'm not going to make a big deal about analyzing this one, but it is, this is a kind of interesting way of doing it, a second way of doing this. Oh, you know what? Someone got 721. Let me do it the other way first, though. So 358. This is so in 7, the places are 1, 7, 49. Sorry, 1, 7, 49. Wait a sec. And yeah, 1, 7, 49. And this last place is 49 times 7, which is, I think, 343. So we have to take away 343 one time, and that's where this first 1 comes from. Now 49s, so it's going to be 4 places. So they're not called decimal places anymore. 15 is too small, so we put a 0 there. And then 15 has 2 7s with 1 left over. So that's why it's 1021. If you got 721, it's because I see now. Actually, 721 has some merit to it in that you can't use 7 because it's only 0 through 6. So in a sense, putting a 7 here is kind of like putting a 10 into that spot. So 721 is actually, it's accurate in the sense of like, it's like squeezing, in their world, 10, the number 10 looks like 7, or 7 looks like 10. Now, as a last question, we'll take that 358 again. But what would happen if you tried to change it into base 12? How many? They're not actually even called digits anymore because digit implies a base 10, but we're going to call it digits still. Okay, so now do one with base 12, converting from base 10 to base 12. Okay, and I see some 25A's. 25A is the answer. Here I did it with subtraction method. 144 is the biggest place because the next one's way bigger than 358. So I subtract away 144 twice. So the number of times I take it away is what goes up here. And then I have 70 left. Well, 70 can be broken up into 5 12s. But then I have 10 ones left over, and 10 is written as the letter A. So that's a skill. And these are the two most important things from today: converting from base 10, converting to base 10, that's easier. Converting from base 10 is a little bit harder. So what else do we have for today? Well, I want to show you how you can do adding and subtracting in other bases. And I'm going to compare base 10 and base 8. And let me see if all my participants are here still. Good, or no new people waiting to get in, because sometimes someone's a little late. So base 10 adding, you add from right to left, 8. When you do 5 plus 7, it ends up being 12, but 12 is too big, so we put a 2 here and we so-called carry the 1. Because this thing was like a 12 before I had to carry the 1. Now 453 plus 275 in base 8. Well, one way you could do this is convert them both to base 10, add them, and then convert the answer back to base 8. But that would take too long. So here's what happens. You do 3 plus 5. But 3 plus 5 is 8. There is no number 8. Just like there's no number 10 when you add in base 10. So what we do is we put a 0 here and we carry the 1. Right? Because 3 plus 5 in the base 8 world is the number that looks like 10 in the base 8 world. And now we do the same thing. 1 plus 5 is 6. 6 plus 7, in our mind, we picture 6 plus 7 is 13. But then we have to think for a second. 13 in base 10 is an 8 and looks like 15 in base 8. Now, people who live in the base 8 world, they would just know that, 6 plus 7 equals a thing that looks like 15. That's just a thing they would know because they'd be good at picturing groups of 8. But we're not going to get that good, and we don't need to get that good. You just do 1 plus 5 plus 7 is 13, but then in your mind say, well, what is 13? Well, it's an 8 and 5 left over, so I put a 5 there, carry the 1, and 4, 5, 6, 7. So 453 in base 8 plus 275 in base 8 becomes 750 in base 8. And I don't know what any of those three numbers are, but if I did convert them to base 10, it would agree. It's like the right answer. But I did it all in base 8. So if you think about why, maybe I should compare this. If I compare it to 3, 7, 8, 6, 4, 2 in base 10. 3 plus 7 is 10, but we can't write a 10 in this place, so we put a 0 and we carry the 1. That carrying the 1 is adding a 10 to these other 10s. In this side, carrying the 1 is adding an 8 to the 5 8s and 7 8s. So there are 5 8s and 7 8s, plus this other 8 that came from adding the 5 plus 3. So this becomes 15, actual 15, carry the 1. So here it is in base Similar question in base 10. Oh, why does 13 equal 15? Why does 13 in base 10 look like the number 15 in base 8? Well, we could do this thing. This is the ones place, this is the eights place. So 13, 8 goes into 13 ones. If I do like that method we've been doing, 13 minus 8 is 5. So 1 8 goes there, but then the 5 is left over. So 13 becomes 15. You know, we practiced with these more complicated ones, but it is true that when you're thinking about small numbers, we sometimes don't like, we try to do it in our head, we kind of lose it for the small one. So that's how you can add in different bases. You can also subtract in different bases. Let's compare the actual 453 minus 275 versus the base 8 version. Like I said before, the base 8 people might call this 453 and 275. They would, you know, they have a different word for 100, but that's how they picture it. So 3, we can't do 3 minus 5, so we trade, we borrow, whatever it is. We regroup, depends how old you are, what they call it. We turn the 5 into the 4, and we change the 3 into a 13, or we stick a little more common to stick a tiny 1 there. Then you can do 13 minus 5 is 8. 4 minus 7 we can't do. We take away one of these hundreds, and we add 10 of them to the tens. So that's base 10 subtraction. Well, base 3 subtraction has the same thing going on. In other words, I can't do 3 minus 5, so I have to borrow, trade, regroup. This 5 becomes a 4. But here's a real thought-provoking question. What does this 3 become? You could type it in. This is one of my favorite questions of the day. What do I do with that 3? So some people said 11, which is right. What would also be a good answer? There's 2 acceptable answers. 11 is a great answer. And let's just show if you do that, because we're adding an 8 to it, so this becomes an 11, and I can continue. But there's actually another answer that's just as good. What is it? By the way, let me continue the question with the 11 idea. Now 1 minus 7 is too small, so I take this, and this 1 turns into, this is all in base 8. So this 1 would turn into a 9 because this 3 was, this is the 64's place, which is 8 8. So I give one of the 8s over to this guy, so I can get it. But yes, I see Nina says 13. So we look at that. Now, I'm going to advise you to do it this other way. This is a great way to do it with the 11 and the 9, but it's not technically how base 8 people would think. Base 8 people would, just like we do, turn the 5 to a 4 and stick a little 1 there. Because that 1 3 is not the number 13, but it's how they represent the number 11. But I'm still going to recommend you do it this way and kind of stick a 9 and 11 there, even though they wouldn't have it. Because if you were at this point here, I see I made a mistake over here also. This 5 didn't become a 1, it became a 4. I don't know what was going on there. So this doesn't become 9 here. Sorry about that. It becomes 12. It becomes 1 5 6. Sorry about that. Anyway, back to here. They would see a 13, and they would know that 13 minus 5 in their world looks like 6, because 13 to them is really, it's all 11 things. 11 minus 5 is 6, whether you're writing 11 as a thing that looks like 13 or not. So they would get the same answer, This 14 is not really 14, it's really the number 12. And kids there would know 12 minus 7 is 5. They're picturing however they picture 12. So they get the same answer. But I'm not going to make you do it this way unless you really feel like you want to like immerse yourself into the base 8 world. I'm going to recommend you do it this way instead. Now, just so you know, when you were little, you probably did something like this: 2 feet 5 inches, or let's say 3 feet 5 inches minus 1 foot 7 inches. And you would have learned, well, the 5's less than the 7, so I'm going to borrow, take 2 here. But don't change this to a 15, change it into a 19 because I traded 1 foot for 12 inches. Not 19, sorry, 17. And then I could actually go ahead and subtract. If anyone ever taught elementary school who's here, they know that lesson, I don't know if they teach that lesson anymore, but it's a very difficult one, and it's doing different basics because we're asking people to think in a different base. Okay, and that's how subtraction works in different bases. Now, multiplication actually works the same way also. Remember I showed you that funny three times table? 1, 2, 3, 1, 2, 3. This looks like 11, but it's really the number 4. This looks like 20, but it's really the number 6. This looks like 100, but it's really the number 9. So if I wanted to multiply in the base 3 world, 211 times 22, which is, we could actually do our standard process. 1 times 2 is 2, 1 times 2 is 2, 2 times 2 is 4, but 4 looks like 11 in their world. Then we do the 211 times this 2, but it's not really a 2, it's a 3, sorry. It's not really a 2, it's 2 3s, so we have to put a 0 here, just like we do in base 10 multiplication, and do the same thing. And then when we add, 2 plus 2 is 4, but 4 looks like 11 in base 3. 2 plus 1 plus 1 is again 4, which looks like 11. And 1 plus 1 plus 1 is 3, which looks like 10. Incidentally, I'm not going to have you do this multiplication. This is just, I just wanted to mention it, but there's no like homework where we do that. I just wanted to show you that it could be done. And those people would only have to memorize basically 4 numbers on their times tables because the others would be obvious. Oh, someone's waiting to get in. Okay, now the next thing, and this is the final thing. So we'll be done by 4 today. And I'm hoping to, like this week, do some live lessons. But because of my scheduling, a lot of times we're going to have videos instead, not live lessons. And I made a chat room, which I'm hoping is like a place you go to if you got an invite to it. And there's like an ongoing chat so that people can discuss the stuff. Because the videos, you know, they're like 5 minutes here, they're not long. Like this lesson that I'm been working on now for an hour and 10 minutes would be like 10 minutes of video when I made it that way. So it's not as good. So the class discussion will fill in some of the gaps, and I'll be participating in the class discussion also. Okay, the final thing for today is an added benefit. So far, we've seen that other bases have more digits, so they don't seem like that useful, although maybe for a computer they're useful because we could store numbers in base 2 or base 8 or base 16. But there is an advantage to different bases, and this comes from decimals. In base 10, 0.125, the 1 stands for tenths, the 2 stands for hundredths, and the 5 stands for thousandths. Well, you can have decimals in other bases. Oh, and by the way, so 1/10 plus 2 over 100 plus 5 over 125, 5 over 1,000, sorry, is 125 over 1,000, which reduces to 1/8. Anyone want to say what they suspect the after the decimal point places are in something like base 8? Yes, the first place is 1/8, is eighths. And yes, the second one is 1/64. And how about that last one? It's a pretty large denominator. It is 5/12. So 1.125 in base 8 is 1. 1's the numerator because there's a 1 there, is 1/8 plus 2 over 64 plus 5 over 5/12. And if we added those together with common denominators, I think we end up with 85 over 5/12. This number, by the way, this is a base 10 fraction. In other words, these numbers are all base 10. This 8.5 is not in base 8. So I'm converting a decimal in base 8 to a fraction. I've never seen anyone make a fraction with base 8 in the numerator and denominator. So here's a question for you. What is just 0.2 in base 3? And yes, it is 2/3. Why is that? What's interesting? Why might someone like me find that interesting? Well, what's 2/3 as a decimal in base 10? Let's go with that question. Yes, the 2/3 is base 10 fraction. That's why there's allowed to be a 3 there. But what is 2/3 as a, yes, it's 0.666 dot dot dot. So a fraction like 2/3 could be a non-terminating decimal in base 10 while being a terminating decimal in some other base. In base 10, 1/2 terminates, 1/4 terminates, 1/5 terminates, 1/8 terminates, but 1/3 does not. But in base 3, 1/3 is 0.1 and 2/3 is 0.2. But in base 3, 1/2 is going to be a confusing thing. Here's a question for you. In binary, 0.1101. This is a base 2 decimal. I'm calling it decimal because I don't know what a good word would be. Can you turn that into a fraction, common fraction, with base 10 number in the numerator and the denominator? Go ahead, take a minute on decimals in base 2. like to write the decimal places: 1/2, 1/4, 1/8, 1/16. And there's only one or none. There's a 1/4, there's a half, a fourth, no eighths, and 1/16. And then if you go ahead and get the common denominators, it is 13/16. Again, that's a base 10 fraction with base 10 in the numerator and denominator. I've never seen a fraction with binary in the numerator and denominator. Okay, the final skill of the day. Oh, I'm just going to give a little kind of note about base 12. In base 10, these are the 4 terminating decimals that are less than 10. But in base 12, 1/2 would be 0.6. In other words, 6/12. And 1/4 would be 3/12. But unlike base 10, we could do 1/3 would be 0.4. So we actually get the third and the sixth while we're at it. It's 2/12. But we don't get a fifth in base 12. Maybe we want to have a fifth. Base 12 actually 1/8 and 1/9 would actually terminate also. I'll show you what those are in a sec. They end up with 2 places. That's why the Babylonians didn't use base 10. They actually didn't use base 12 either because they want to have a fifth. The Babylonians could have used base 30. 30 is a good base because you get 1/2, 1. Oh, yeah, 30's, sorry, 30 gets you fifths, but it doesn't get you fourths. That's why the Babylonians used base 60. Which seems really difficult, and it is actually pretty hard. Tomorrow will be about base 60. But I just want to mention these things. Here comes the last skill of the day. The last skill of the day is how to convert something, how to convert a fraction into a base, into some other base. So like 7/9 is the fraction. I want to make it base 3. And sorry, I don't have a fancy, the Apple Pencil, so I'm using my finger. So my handwriting is pretty bad on these. Luckily, this skill is kind of fun to do. Here's the way you convert 7/9 into base 3, like a decimal. I think my finger's getting tired also. A lot of excuses. Here's how you do it. You set up a proportion where you put the base down here. And you cross multiply. And you solve. And you turn it to a mixed number. If you could reduce, that's even better. And yes, this method will work for base 12. You put, whatever number you put there. Now we're not done yet. The whole number part of the answer is the first place in the base 3 number. But because there's a remainder, you then take that remainder and we set up a proportion. And again, we put the 3. So 7/9 equals x over 3. 1/3 equals y over 3. Y ends up equaling 1. And that is no remainder. And this answer is finished. So it's kind of fun to change from starting with a fraction to change it into another base. Since I kind of left you hanging over here with what's 1/8 in base 12, let's have you take a minute. So we want to change this into base 12. Go ahead and do the proportion, and you'll get a whole you get a whole number. Let's take a look. Whoops. Equals x over 12. So it didn't end because I end up with this remainder, but the 1 ends up being the first number after the decimal point. Then you take the 1/2 equals y over 12, and y ends up equaling 6. So 0.16 is 1/8 in base 12. So it terminates also. So base 12 is really nice. You can't do 1/5, but you can do a half, a third, a fourth, a sixth, an eighth. Oh, somebody's coming in on a phone. And here's a fun question to end with today. What's 1/2 in base 3? I don't think it will be 1.5 because 1.5 is bigger than 1, but 1/2 is less. Okay, and I see, hold on. Okay, everybody. So I saw a couple of different answers, and the 0.111 is the answer because we have our decimal here. 1/2 is less than 1, so they can't be anything over here. But when we do x over 3, 3 equals 2x, x equals 1 and a half. So the 1 goes here, and so somebody said 1.5 before, that's what the x value is, but the first digit of it goes there. But now notice how there's a half there. So if I continue the process, this is going to happen. And it's the same question as before. So y is also going to be 1.5. And that's why, yes, 1/2 in base 3 would be an infinite repeating decimal like that. Tomorrow we'll learn the ins and outs of base 60, where it doesn't have a lot of repeating at all because 1/5 does not repeat in base 60, but not for today. Okay, so that's what I wanted to show you today. There's a homework assignment, and there's also this Delta math assignment. Try to do those both. They shouldn't take too long. If you also take a chance to go, if you got an invite to that Google, I think it's called Hangouts, see if you could type something on there. I'd love to have that as like a thing. Delta Math, there is a, let me go to the class website. Let's see. There's instructions for, oh, and someone's trying to get in. There's instructions for Delta Math. Let me get, we're over here. So if I go back to the class itself, down here, oh, maybe it's into the stream. I see. Okay, I need to post that. I thought I posted it, but apparently I didn't. So I will send instructions for.
No, you did post it. It's there because I did it from there.
Oh, where is it though? It's not on materials. Was it in the stream?
Yeah, I think it's in the stream. Lower down.
Ah, thank you. There it is. Thank you very much. So here are the instructions. There's you create an account, you put this access code in, and you pick City College math teachers, and it has a little assignment. It makes you get 5 questions right, and it's just about changing integers into base 10 and back. It's not, and there's no base 12 or anything like that. It's just base is smaller than 10, so it won't take you too long, but it's a really good way for me to check if you mastered the material. Okay, so that will be good for today. I think I'll try to, I'll let, basically every day, I'll let you know if there's gonna be a live class as early as I'm able to. And if there's not a live class, there'll be a video for you. And that, you really probably wanna be discussing with people, you know, on that group chat, because this is confusing. It's mind bending, you know, different bases, but in this math teacher version of the course, I'm trying to keep. Oh, you won't have to do a symbol for the base in the Delta Math.
Could you please send the link to the groups to our Google Classroom emails, because the original email that you sent, I was unable to click the groups because it's not a Gmail email.
Yes. Could you
the problem also getting in?
Could you send me a Gmail address then? And because I could add you to the group from a Gmail address, but there's not, as far as I've been able to tell, like a way to send an invite to that thing. It's called like Google Hangouts. And if you send me a Gmail address, I can add you to it.
Okay.
But I can't, apparently, I haven't found a way to make a link invite. I can invite somebody if I know the email address, but I could also just add them if I have it.
Okay.
And yes, for the work, yes, I want to see the work for the homework, the work shown. The Delta Math, you don't need to show your work for that, but for the written work.
Also, when we have live classes, are we still also watching the videos that you put up on YouTube or no?
Oh, you wouldn't need to for those times.
Okay.
The videos are pretty short. They're like for this whole hour and a half class that we did. The videos are only maybe 10 minutes total. So you might watch them just for reinforcement, but no, you wouldn't need to watch them if we ever have a live class. Okay, and I'm gonna put myself on mute and keep the class open if people want to chat to each other while I don't want to close out because I have the, in this chat, I see a bunch of emails that I'm gonna add right now. So I'm gonna mute myself, but I'm gonna come back in 5 minutes.
Hi, I'm having internet issues. Can someone please tell me if he said anything about the books?
No, nothing else.
No.
There you go. I'm still here. The book is optional. Those books are excellent books, and all the material I'm doing comes from those books. But there's not going to be, for instance, reading from the book as a homework assignment or any like work like from the book. You could learn everything from these videos and from my lessons, but the book is quite a good resource that I put out there. It's a great book to have. Some of this material gets pretty hard, and having it in a book form, since these topics are kind of obscure, and if you search for them on the internet, you might get some really complicated explanations of them once we start getting to the history tomorrow. So I love those books, but if you didn't have the books, you could survive without them. Okay, I'm going to go back on mute.
All right, thank you.
So there's homework. We have to scan and add up, well, submit via Google Classroom.